Welcome back to our lecture series. We are now going to discuss solution of quadratic inequalities by using absolute value theorems. The first two methods that we have discussed, a solution by interval method and solution by using two theorems, are somewhat limited because they will be more conveniently used when the given quadratic inequality is factorable. We can actually solve the solution set of any quadratic inequality by using absolute value theorems. Let's consider again these inequalities. Ax squared plus bx plus c greater than 0 and ax squared plus bx plus c less than 0. In both these inequalities, we know that a, b, c are any real numbers and a is not equal to 0. Our object here will be to write this inequality here in the form a square greater than, let's say, a number p. Okay, and here the same thing, we want to write that inequality in the form square here less than a number p. If you are given the inequality and you have already transformed it to this form here, we don't really need to consider going further to solving the solution set if p here is negative. Because if p here is negative, it is trying to say that triangle squared is greater than a negative number. And we know that the square of a quantity will always be non-negative. This means it should be greater than a negative number for any value of the variable here in this expression. What I'm trying to say here is, if you have reached this point and you get a p which is negative, you don't need to go ahead and solve the inequality because we already know this one here. Triangle square is greater than a negative number, meaning our solution set should be all reals. Because now we have this statement which is always true. That is, a square is always greater than a negative number because a square can only be a non-negative number. On the other hand, if p is negative or triangle squared is less than a negative number, then our solution set is already a null set. So you don't need to proceed. Why? Because a square here will never be less than a negative number. A square here will be at least 0. And 0 is still what? Greater than a negative number. So, to apply solution using absolute value theorems, we have to make sure that what we arrive at here will be positive numbers so that we can proceed in using absolute value theorems. Okay? So, here, the theorem that we will use here will be, okay, suppose absolute value of x is greater than k and k is greater than 0, then this means that x is greater than k or x is less than negative k. Okay. On the other hand, if I have here absolute value of x is less than k and k is greater than 0, then I have what? X should be in between negative k and k. Again, we are using this theorem. If what we arrive here at this statement here is a positive p here. If we have arrived at a negative p, then we don't need to continue solving using this theorem, because by then we know that this statement will always be true for any value of x. Okay? Similarly, this one will never be true for any value of x, because a square, again, I say, is not less than a negative number. Let's illustrate what I'm trying to say. Example here. Suppose I have here x squared minus 2x plus 3 greater than 0. Okay? X squared minus x plus 3 greater than 0. Our aim is to arrive at this form. Triangle squared greater than a certain number. So how do we do that? Let's do completing the square here. I know that I can have this transferred to the other side. And now, what will make this a perfect square trinomial? That will be a plus 1. And this one is a plus 1. And then I can now write this as what? X minus 1 squared greater than a negative number. So, I don't need to get to this theorem to be able to conclude the solution to this given inequality. Here, this is a square and it's greater than a negative number. So for any x that you will get here, this left hand side will always be greater than a negative number. In fact, the least value for this expression will be 0. That happens when x equals 1. 1 minus 1 is 0. So 0 is still greater than negative 2. And any other x values will make this expression greater than 0, which is greater than a negative number. So here, therefore we say that our solution is what? All real numbers. Or this is an absolute inequality, meaning this is always going to be true no matter what x real numbers you will substitute on the left hand side. The left hand side will always be greater than 0. Hence it is real. Now, if you look at the other side here, and I will solve this inequality here less than 0, I can complete the square again, and I can transfer this to the other side, and what completes this one will be plus 1, and then we have a plus 1, and I get here x minus 1 squared less than negative 2. Here, I don't need to proceed using the absolute value theorem here again, because this number here now, this number here is already a negative number. And if you look at this statement, this squared number can never be less than a negative number. Okay? Because the least value for this number is 0 when x is 1. 0 is not less than negative 2. Therefore, we cannot find any value of x that will make this true. Okay? Okay, so if our solution set here is all reals, then here there will be nothing in our solution set. Meaning, there will be no x that will satisfy this inequality. Okay, the first two examples are actually extreme cases, which means they are trivial cases. We can always determine almost immediately the solution if you are already at this point of your solution. Okay, let's try to find out if we can use this in the next example. Okay, so let's see. Suppose I have here x squared minus 2x minus 3 greater than 0. Okay, x squared minus 2x minus 3 greater than 0. Now, our objective here is to be able to write this statement here in this form. Triangle squared is greater than some number. Alright? So, completing the square, I'm now going to have again x squared minus 2x, and then this is 3. What will complete this? Is still plus 1, and this one is a plus 1. Okay? Now, I will have this as a square of a binomial, and this will give me a positive number. So, this is a positive number, so we can go on and apply this theorem. But how do we apply this theorem? We will just have to introduce what? The square root symbol here, so that this one now can be written as absolute value. Absolute value of x minus 1, okay, is greater than 2. Here, my x here is this whole quantity here, and my k is 2, which happens to be greater than 0. Which means that the solution to that inequality now, okay, may erase this. We now have this inequality here, and according to this theorem, I can remove the absolute value symbol by rewriting the statement in this form. And I will get here x minus 1 greater than 2 or x minus 1 less than negative 2. This is s greater than k or x less than negative k. Our k here is 2. Okay? Solving these two inequalities, we get x greater than 3 or x less than negative 1. In terms of interval form, I have here, I'll write this first, from negative infinity to negative 1, union from 3 to positive infinity. That's the solution set of this inequality. Or you can graph your solution set. I have here 3 here, I have here negative 1. X less than negative 1 is going to the left, or x greater than 3, this is going to the right. This is the graphical form, this is the interval form, and you can have this your set form. Okay, now let's find out if we will solve the other direction. Okay, what if we have the other direction? Let's have another one that does not give you a perfect square here. So we have here, for example, x squared minus 2x minus 5 less than 0. Again, our goal here when we use absolute value theorem is to be able to come up with a statement with a perfect square on one side and a constant on another side. Let's have this. I have here x squared minus 2x, and then I'll transfer 5 there. And then I'm going to have what? Plus 1 here. That completes this as a perfect square trinomial, and then I'll add plus 1 on the other side. And I can now write x squared minus x plus 1 as x minus 1 squared less than 5 plus 1 is 6. So this statement here follows this one here, where the left hand side is a square, right hand side is a positive number. So now we can use this theorem. Okay? So absolute value of x less than k, k greater than 0 means that x is between negative k and k. Okay, before we can use this theorem, we have to rewrite this in its absolute value form. So I will introduce the square root, I will introduce the square root. And now this one can be written as absolute value of x minus 1 less than square root of 6. Okay, from the definition of absolute value, the square root of x minus 1 squared can now be absolute value of x minus 1. Okay, and let's simplify that. Simplifying absolute value of x minus 1 less than square root of 6, following this theorem, we now have here x minus 1 in between and negative square root of 6 here, and here positive square root of 6. In this theorem, my k is equal to square root of 6. It is greater than 0. Okay? So we just remove the absolute value and rewrote the statement in this form. Okay? Now we look for x here. I need to remove negative 1 at the middle. So I'll have plus 1 to all sides of this inequality. And I will get here what? 1 minus the square root of 6 less than x, and then have 1 plus square root of 6. Okay? I can have this my set form. Okay? That's my set form. Now, how will I write it in graphical form? Okay? This is the smaller critical number, 1 minus the square root of 6. Okay, this one is open. And this is 1 plus the square root of 6 is also open. So, the solution here will be all points between these 2 points. So, there are infinitely many of them that will satisfy the given inequality. This is the graphical form, and I can have my interval form as open at 1 minus the square root of 6, and then open at 1 plus square root of 6. So these are equivalent ways of writing your solution set of the inequality, this inequality here. Okay? So, that's solution by using absolute value theorem. So to recap, what did we say? We want to arrive at a statement where we either have triangle squared greater than p or triangle squared less than p. Okay, less than p. Now, if initially we said here, if p is negative, then this one will always be true. I mean, a square is always greater than a negative number for any value of the variable here. So, if p is negative, then our solution set is all R, which means we have an absolute inequality as we have explained. However, if p is greater than 0, then you can proceed using this theorem. This theorem here, absolute value of x greater than k implies x is greater than k or x is less than negative k. On the other hand, if we are solving a less than inequality and initially this statement gives us p less than 0, then our solution set is already null set, meaning a squared number can never be less than a negative number. That's why the solution set is null set. However, if p is greater than 0, then you can proceed using this theorem. Okay, absolute value of x less than k implies x is between negative k and k, as we have illustrated. Okay, so that's how to use absolute value theorems when you solve quadratic inequalities. Thank you and see you at the next session.